Today's automotive engines are complex systems of precision components assembled to very fine tolerances. Accuracy and precision are essential when it comes to building an engine. And they're just as essential when it comes to servicing that same engine when it's brought to the dealership for repair. Later on in this program, we'll take a look at some of the practices and procedures you should be using when you service engines. But the first step in our back-to-basics approach is diagnosing the problem when the vehicle is brought in. When a customer's vehicle is brought in for repair, the first step in a 6-step troubleshooting sequence is to verify the customer's complaint. In this case, the customer complains of high oil consumption. Even though this particular problem can be difficult to verify, your diagnosis should always begin with a thorough visual inspection. Oil leaks are a common cause of high oil consumption, so begin by checking for oil or other fluids dripping from the vehicle. If you do find a leak, check the color of the fluid being lost. Engine oil will be amber or black. Coolant will be green. Automatic transmission fluid will be red. Manual transmission fluid will be amber. Power steering fluid will also be amber. If the leak is engine oil, check for oil being blown out from a loose dipstick. An effective way to find leaks is by adding fluorescent dye to the oil. Because of the large number of additives in today's oil, we recommend that you add 2 ounces of dye. If the oil is excessively dirty, or if it contains graphite or molybdenum, you may need to add additional dye. Start the vehicle and run the engine for several minutes to allow the dye to thoroughly mix and circulate with the oil. Then, use a black light to examine suspected areas. Leaks will show up under the black light as a bright yellow glow. If the oil leak doesn't show up after running the engine for several minutes, you may want to return the vehicle to the customer and have them bring the vehicle back in to be rechecked after the oil level is down a quart. Another way that oil can be lost is through burning it. This usually indicates an internal problem with the engine, such as broken or worn piston rings, worn valve guide seals, or worn valve guides. It may also indicate a blocked PCV valve. If oil is getting past the rings or through the valve guides, it usually shows up as a black oily deposit in the end of the muffler tailpipe, or as blue smoke out of the tailpipe. If you added the fluorescent dye, use the black light to check the tailpipe for leaking oil. If this test failed to reveal the cause of the problem, the next step would be to perform a compression test on the engine. Before performing this test, make sure the battery is fully charged to ensure adequate cranking speed. Beginning with the cold engine, start and run the engine for 5 minutes to warm the combustion chambers. After 5 minutes, stop the engine and remove all the spark plugs. Never use an impact wrench to remove spark plugs. Use only hand tools and proceed with caution. Next, block the throttle in the wide open position. On vehicles with a conventional ignition system, disconnect the coil wire from the distributor and connect it to a good ground. On vehicles with a direct ignition system, disconnect the coil connector. This is necessary to avoid a fire hazard from arcing spark plug wires. Install the compression gauge in a spark plug hole. Crank the engine through 1 full compression stroke. Record the reading. Release the pressure from the gauge. Crank the engine through 1 more full compression stroke. This is to check for a sticking valve or a worn valve guide. Again, record the reading. Release the pressure from the gauge. Crank the engine through 5 full compression strokes. Repeat this procedure for all the remaining cylinders, recording your readings as you go. Compare the readings obtained and note the cylinder readings which vary more than the allowance specified in the service manual. Usually, the lowest cylinder must be at least 75% of the highest. Now let's look at the procedure for performing a wet compression test. A wet compression test is taken to determine the cause of the low cylinder pressure readings obtained during the dry compression test. During the wet compression test, a tablespoon of 30-weight oil is squirted into the cylinder with the low reading. The oil temporarily seals the gap between the piston rings and the cylinder wall. So if the problem lies in the rings, the wet test should show compression figures similar to those recorded by the good cylinders. The oil will not seal a leaking valve or head gasket. So if the cylinder compression was still reading low, the problem lies in one or both of these areas. Another way of testing a cylinder is to perform a cylinder leak down test. This is easier to perform than the compression test, but it requires a cylinder leak tester, such as this one. The leak tester is threaded into the spark plug hole after the piston has been brought up to top dead center on the compression stroke. The cylinder is then filled with compressed air. The gauge on the leak tester shows the percentage of leakage. Anything over 20% leakage shows a need for engine repairs. While the cylinder is filled with compressed air, it's possible to pinpoint the source of the leak by listening for the hiss of escaping air. Air leaking past the intake valve can be heard at the carburetor or throttle body. Air leaking past the exhaust valve can be heard at the exhaust tailpipe. Air leaking past the piston rings can be heard at the oil filler opening. Also listen at adjacent cylinders for air leaking through a blown gasket. Remove the radiator cap and look and listen for bubbles or escaping air, which indicates a crack in the block or gasket leakage into the cooling system. Now let's look at a case where a customer brings in a vehicle because of an engine noise. According to the repair order, the customer has brought in this vehicle because of an engine knock during startup. As always, the first step is to verify the customer's complaint. In this case, it's also important to find out if the knock only occurs when the engine is cold, or if the knock persists once the engine has warmed up. Using an engine stethoscope can help pinpoint the problem without having to disassemble the engine. If you believe the engine knock is the result of piston slap, isolate each piston in turn by electronically canceling each cylinder using an engine analyzer. Caution, don't do this for long, as it will heat up the catalytic converter. If the noise goes away, you've located the cylinder that's producing the engine knock. Based on the results of the test, you can then decide whether the engine will require disassembly or not. Later in this program, we'll be showing you the basics of engine service, including disassembly and assembly. But first, we'll cover a skill that's essential to professional engine service: measurement. Before we go any further, let's take time out to discuss measurements. As we saw at the beginning of this program, modern engines are built to exacting tolerances. Because of this, it's essential to be able to measure components accurately. Here's a sample of some basic measurement tools you should know how to use: a good straight edge, feeler gauges, a micrometer, a dial indicator, and a cylinder bore gauge. To check cylinder heads and engine block surfaces for warpage, you'll need a precision straight edge. In this case, you can throw away your 1-foot wooden ruler. The straight edge is a steel bar with precision ground edges. It needs to be at least as long as the cylinder head itself, if not longer. Be careful when handling and storing a straight edge. It must not be damaged. To check a cylinder head for flatness, place the straight edge along the head. Then sight along the straight edge to see if there is any warpage. If there is, use feeler gauges to measure how much warpage is present. Make sure the surface is clean and all gasket material has been removed. Then check the head using the following pattern: measuring and recording the amount of warpage, if any, at each location. In our case, this head has about 2/1000ths of an inch of warpage, which is within tolerances. If we measured more than 4/1000ths of an inch of warpage, the head would have to be sent out to be resurfaced or replaced. Check your warranty policy and procedure manual for recommendations. While we've got our straight edge handy, it's a good idea to check the cylinder head bolts for necking. To check for necking, hold a straight edge against the threads. If all the threads contact the straight edge, the bolt is good. However, if the threads are not aligned even with the straight edge, the bolt has been stretched or necked down. Because a stretched bolt is weaker, it should be replaced. Our next measuring tool is a micrometer, or a mic as it's often called. Many of the newer micrometers feature a digital readout. However, it's still important to know how to read a vernier scale micrometer. The basic parts of a micrometer are the frame, anvil, spindle, sleeve, and thimble. A scale on the sleeve of a micrometer reading in inches is divided into 40 graduations, each one equal to 25/1000ths of an inch. Every revolution of the thimble uncovers one division on the sleeve. Every fourth division represents 1/10 of an inch and is numbered. The beveled edge of the thimble is marked in 25 divisions. Each division represents 1/1000th of an inch. So one rotation of the thimble moves the spindle 25/1000ths of an inch. Here's how to read the micrometer. In this example, the thimble edge has moved across the sleeve past the number 5, or 500,000ths, plus 3 more sleeve marks. Each sleeve mark is 25/1000ths of an inch. So the sleeve shows 575/1000ths of an inch. The edge of the thimble aligns at 12, showing 12/1000ths. So adding 12 to 575, we get a total reading of 587/1000ths of an inch. If the micrometer is capable of reading to 10/1000ths of an inch, it will have a vernier scale here on the sleeve. The vernier has 11 lines marked from 0 to 10. When the thimble marks do not fall in line with the long sleeve mark, indicating a fraction of 1/1000th of an inch, carefully examine the vernier lines. One of the vernier lines will be aligned with one of the thimble marks. When you determine which one it is, that vernier line indicates the number of 10/1000ths to be added to your initial thimble reading. Let's see how this works by taking a reading you'll need to make to correctly size pistons during an engine overhaul. Up until now, we've been using an inch micrometer. Ideally, you should have a set of 6 micrometers, covering a range from 0 to 1 inch up to 4 to 5 inches. As always, you should check the service manual for the correct sizing location, as this can vary depending on piston design. Once you've determined the correct sizing location, hold the micrometer with one hand. With the other hand, use the thumb and forefinger to tighten the spindle. It's important to make sure that the mic is held at right angles to the piece you're measuring. If the mic is held cocked, you'll get an oversized reading. To avoid this, hold the mic loosely and gently turn the spindle down against the workpiece. Remember, the micrometer is not a C-clamp. Use a minimum of pressure. If the micrometer has a ratchet at one end, use it. The ratchet prevents over-tightening, which can bend the frame, producing incorrect readings. The workpiece must slip through the micrometer with a very light force. When you're satisfied with the adjustment, read the micrometer setting, being careful not to move the adjustment. If the micrometer has a lock, use it to lock down the reading. Once you have the reading, record it immediately. In fact, the best technique is to take 3 readings and then use the average. Micrometers have hundreds of uses in engine service, so it's vital that you know how to use one. Another essential measuring tool is a dial indicator. A dial indicator is a precision tool designed to measure movements in thousandths of an inch or in hundredths of a millimeter. Dial indicators come in a wide variety of mounting styles and measuring ranges. One of their most common uses is checking end play in crankshafts. When using a dial indicator, make sure that you mount it to something firm, such as the engine block, rather than the car body, which can flex and cause faulty readings. Keep the support arms as short as possible for a rigid mounting. It's also vitally important to make sure that the indicator is set up exactly perpendicular and parallel to the center line of the shaft. In this case, the indicator is not set up parallel to the workpiece, giving a false reading for crankshaft end play. A more specialized form of dial indicator is a cylinder bore gauge. Along with a micrometer, this tool is essential to accurately size pistons. Two readings are taken at 90 degrees to one another at 3 heights in the cylinder bore. The first 2 readings are taken at the bottom of the bore below the ring travel. 2 more are taken in the middle of the bore. And then 2 readings are taken at the top of the cylinder bore just below the ring travel. The readings are recorded as they are taken and then can be used to determine cylinder bore taper and out of round. These specifications will vary from engine to engine. Pistons can then be sized to the bore by subtracting the piston size from the bore dimension measured halfway down the cylinder bore at 90 degrees to the crankshaft center line. Check the diagrams in the service manual for both locations. Another measuring tool you need to be familiar with is Plastigauge. The Plastigauge method is a system for measuring crankshaft bearing clearances. The measuring technique we're about to show can be used if the engine is on an engine stand. If you're measuring main bearing clearances with the engine still in the vehicle, you'll need to refer to the shimming procedure outlined in the service manual. Remove the bearing cap and bearings from the bearing to be checked. Then clean all traces of oil from the crank. This is very important for accurate readings, as Plastigauge is soluble in oil. Next, place a piece of Plastigauge across the entire width of the crankshaft journal, approximately 1/4 inch off center and away from the oil hole in the bearing cap. Then replace the cap and torque to specifications. Do not rotate the crankshaft while assembling the cap, or the Plastigauge will be smeared, giving inaccurate results. Remove the bearing cap and compare the width of the flattened Plastigauge with one of the scales provided with the package. Plastigauge generally comes with 2 scales, one in inches, the other metric. Whichever scale you use, locate the band closest in width to the flattened Plastigauge. This band shows the amount of clearance. Record all readings taken. Well, that was a brief look at just some of the measuring tools and techniques that are needed when working on today's precision assembled engines. When we come back, we'll go into more detail on engine service, including disassembly and assembly techniques. Despite the wide variety of engines in service today, there are certain basic techniques and practices that apply to them all, regardless of design. That's what we'll be covering in this part of the program. We'll start by looking at cylinder heads. To avoid damaging threads, never use an impact wrench to install or remove cylinder head bolts. This is especially true on engines with aluminum blocks or heads. Always use hand tools to install and remove cylinder head bolts. Also, to avoid warpage, the engine should be cold before the cylinder head is removed. Cylinder head bolts should be removed in steps, following the reverse order of the tightening sequence to prevent warpage. Once you've got the head off the engine, you can check it for flatness, as shown earlier. Before that, however, you'll first have to remove any remnants of the old gasket. To do this, you'll need a scraper and a cleaning solvent, such as Mopar gasket remover. First, check the material of the cylinder block or head that you're cleaning. If it's aluminum, you must only use a wood or plastic scraper. Never use a metal scraper on aluminum. It could leave a gouge that no gasket could ever seal. If the block is cast iron, it's okay to use a metal scraper, although it pays to be careful no matter what kind of metal you're dealing with. The sealing surfaces on even cast iron blocks can be damaged by overly vigorous use of abrasives. An important part of any professional engine disassembly is the correct marking of engine parts. Components, such as bearing caps, should be number stamped before removal. If the proper direction of installation isn't indicated, add an arrow. Also, valve train components, particularly rocker arms and lifters, or cam followers as in this case, must be numbered and kept in the proper order for reinstallation. If the pistons are to be removed and they don't already have an identification arrow, it's a good idea to use a grease pencil to number the pistons and also to draw a reference line from the pistons to the cylinder block. Other tips include just general good housekeeping, making sure the area where the engine work is being performed is as clean as possible. Dirt and other contaminants in the workshop will quickly find their way into disassembled engines. Because of his dirty workbench, this tech is building thousands of miles of wear into the engine he's servicing. Even in clean workshops, it's a good practice to stuff clean shop towels into open cylinder bores to keep out dirt and other contaminants in the air. Another good practice is to closely track each nut and bolt removed by placing them in plastic bags with masking tape labels. This prevents wasting time searching for lost or misplaced fasteners. Because they are machined in place, it's vitally important that items such as camshaft bearing journal caps, if not already marked, are marked for location and direction before they are removed. Once again, you should never use an impact wrench to remove camshaft bearing cap bolts. Use hand tools and remove bolts in steps, following the reverse order of the tightening sequence. When the camshaft is removed, it should be measured using a micrometer. Using the mic, measure lobe diameter in two places at the larger diameter. Take the first reading with the micrometer in the unworn area at the edge of the lobe. Then take the second reading in the worn zone where the rocker arm or roller follower contacts the lobe. Subtracting the second reading from the first gives you the amount of lobe wear, which should not exceed the specifications listed in the service manual. If the camshaft is not to be replaced immediately, it should be wrapped in a clean cloth and placed somewhere safe. Just throwing it under a workbench to collect dust is not a good idea. Before reinstalling, make sure the camshaft and head are clean, the bearing cap bolts are correctly torqued, and that the camshaft turns. After the camshaft has been reinstalled, a dial indicator should be used to check end play. Using a screwdriver, pry the camshaft as far rearward as it will go. Zero the dial indicator. Now, move the camshaft as far forward and rearward as it will go. End play travel should not exceed the specifications listed in the service manual. At the beginning of this program, we looked at two techniques for diagnosing high oil consumption, a compression test and a cylinder leak down test. If either of these tests indicated a leak past the intake or exhaust valves, you'll need to inspect and measure both valves and valve guides for wear. Valve guide wear can be measured using a dial indicator. Position the valve head about 4/100 of an inch above the cylinder head gasket surface. Now try moving the valve towards and away from the dial indicator. Readings should be taken both lengthwise and crosswise across the cylinder head. If the dial indicator reading exceeds the specifications listed in the service manual, you will need to ream the guides for valves with oversized stems. The stem diameter of the valve should be mic'd in the valve guide area and checked against the minimum dimensions listed in the service manual. The valve margin and valve face should be inspected for wear or damage and refaced if necessary. Before removing pistons, connecting rod bearing caps should be numbered and arrowed for direction. Relieve torque evenly by loosening the nuts in steps, following the reverse of the tightening sequence. Before pulling the piston and connecting rod out of the block, cover the connecting rod bolts with short lengths of rubber hose. This will prevent scratching the crankshaft journals. Also, check the cylinder for a ridge. Use a ridge reamer if necessary. Once removed, give the piston a thorough inspection for damage. Check the piston crown for damage caused by broken components. Check the piston skirts and lands for scuffing. Also check for worn or broken rings. Use the measuring procedure shown earlier to size the piston. If you don't have the correct tools for piston removal and installation, send the piston out to a machine shop. While there, have them check the connecting rods for bend and twist. Under no circumstances should you ever attempt to remove a piston by heating the piston with a torch and then beating the piston pin out with a mallet. This will heat treat the piston, damaging both it and the piston rings. Similarly, to avoid damage, piston rings should only be removed and installed using a suitable ring expander tool. Use a piston ring groove cleaner to remove carbon deposits from the ring grooves. Measure the piston ring side clearance by laying a new piston ring in each ring groove and slipping a feeler gauge between the ring and the edge of the ring groove. Be sure to use the correct ring for each groove. They are different. If the groove clearance is greater than specified, new pistons will have to be used. The cylinder block should be prepared by washing the bore and crank journals with warm soapy water and then rinsing. This step is very important and shouldn't be ignored. Failure to clean the cylinders properly will cause rapid engine wear from the moment the engine is started again. Thoroughly dry the area with compressed air, and then check the cylinder for residue by wiping with a clean rag. If the rag picks up dark smudges, you'll have to re-clean the cylinder. After the cylinder has been thoroughly cleaned, lubricate the bore with SAE 30-weight oil. Before installing new piston rings, the ring end gaps must be checked. Insert the top ring into the cylinder and square it up with the cylinder walls by pushing it in with the top of the piston. The ring should be near the bottom of the cylinder at the lower limit of ring travel. To measure the ring end gap, slip feeler gauges between the edge of the ring until the gauge equal to the gap width is found. The feeler gauge should slide between the ring ends with a slight amount of drag. If the gap is too large or too small, recheck cylinder bore dimensions and the ring kit size for discrepancies. Piston rings should always be installed using the correct ring expander tool. Install rings with the ID mark facing up towards the top of the piston. Be sure to check the service manual for the correct ring installation order, as this will vary with application. Lubricate the piston head and rings by immersing them in clean engine oil. Place short lengths of rubber hose over the connecting rod bolts to protect the crankshaft journals from scratches. Making sure that the piston ring end gaps are staggered, as recommended by the service manual, put the piston connecting rod assembly in a piston ring compressor. Install the piston into the engine, using the arrow on the piston crown for reference. The piston can be gently tapped into the cylinder bore, using the end of a wood or plastic hammer handle. After all the connecting rod caps have been torqued down, use a feeler gauge to check the connecting rod side clearance at each journal. Refer to connecting rod specifications in the service manual. The last section in our Back to Basics look at engine service concerns torquing procedures. Many engines now use torque-to-yield bolts, which must be tightened in a special sequence. One way to tell if the engine you're working on has torque-to-yield bolts is by a visual inspection. Torque-to-yield bolts have a thread depth roughly twice that of a regular bolt. It's important never to mix regular bolts with torque-to-yield bolts. Although bolt tightening procedures are often overlooked in the field, tightening fasteners to the correct torque in the correct sequence is just as vital to engine longevity as any of the other procedures covered in this program. Let's start by taking a look at the cylinder head bolt tightening sequence on the 3-liter PRV engine. Of course, you'll need a torque wrench for this. If you have access to a click-type torque wrench, it makes the process a little easier and quicker to perform. In the service manual, you'll find several different cylinder head bolt tightening procedures, depending on the engine serial number. We will only be showing the procedures used on engines up to and including serial number 89615. Be sure to check the serial number of your engine and then refer to the manual for the correct tightening sequence. Starting with the number 1 bolt in the sequence, tighten all bolts to 44 foot-pounds of torque. The following procedure is then performed on all bolts, one at a time. Starting with bolt number 1, completely loosen all bolts. Then tighten bolt number 1 to 15 foot-pounds of torque. Install the graduated disc tool, number 7321 or equivalent, between the socket and the torque wrench. Set the tool. Then turn the dial to 0 degrees. Then angle tighten bolt number 1 in the sequence to 106 degrees, plus or minus 1 degree. Repeat this procedure for all the remaining bolts in the sequence. For further training on engine service procedures, Chrysler Service Training offers a number of courses. For a complete list of courses, check the Technical Training Course Selection Guide or refer to the reference manual accompanying this videotape. That's all for now. We'll see you next time on VideoTec.
The safety recall detailed in this program involves vehicles equipped with the anti-lock brake system. Included are late 1990 model year and all 1991 model year AC and AY body Dodge Dynasty, Chrysler New Yorker, Fifth Avenue, and Imperial passenger cars. Also included are 1991 model year AS body Plymouth Voyager and Grand Voyager, the Dodge Caravan, Grand Caravan, and Caravan CV models, and the BB body Dodge Monaco and Eagle Premier passenger cars. On involved vehicles, the crimped end fitting of the anti-lock brake system high-pressure hose may leak or blow off. To correct this condition, ABS high-pressure hoses on all involved vehicles must be visually inspected to identify the hoses with crimped end fittings for replacement. Service replacement hoses, which have been available from the parts supply depots for the past few months, have formed ends and do not need to be replaced. For repair of affected vehicles, a quantity of parts will be distributed initially and billed to all involved dealers to cover a portion of the total vehicles involved. Depending on the vehicle model, one of 3 recall parts packages will be required. For BB body Eagle Premier and Dodge Monaco models, use recall part number C3940-468. For all AC AY body Dodge Dynasty, Chrysler New Yorker, Fifth Avenue, and Imperial models, use recall part number C3940-469. For AS body Plymouth Voyager and Grand Voyager, Dodge Caravan, Grand Caravan, and Caravan CV models use recall part number C3940-470. Most steps of the following service procedure are similar for all involved vehicles and will be demonstrated on a 1991 AS body vehicle. For Eagle Premier and Dodge Monaco, the high-pressure hose replacement procedure requires several additional steps, which will be shown separately later in this program. To begin the service procedure for all involved vehicles, you must first determine if the vehicle requires the recall service package by inspecting the high-pressure ABS hose that is on the vehicle. To check the hose, look at the hose end fitting at the hydraulic assembly. If the hose to fitting end has a formed end, as seen in this example, the hose has already been replaced and does not require replacement again. However, if the hose to fitting end has a crimped end, as seen here, the high-pressure hose must be replaced with the applicable recall service package. On BB body vehicles, the hose to fitting end is located close to the hose mounting bracket on the left shock tower. To begin the hose replacement service procedure, the system pressure must first be pumped down before any pressure lines are loosened. You should be aware that the normal working pressure of the ABS boost system is 1,650 to 2,050 psi. Failure to reduce the pressure could result in personal injury. To reduce the system pressure, turn the ignition switch off and apply the brake pedal 45 to 50 times until the pedal becomes firm. Next, with the ignition still off, disconnect the negative battery terminal. Now remove the fresh air intake duct from the vehicle. On AS body minivans, you will also have to remove the air cleaner assembly. For AC/AY body vehicles, the transmission tuning weight, located near the pump and motor assembly, should be removed to provide access to the pump and connector block fitting. Next, on all models, clean the connecting points for the high-pressure hose. Use Mopar brake parts cleaner, part number 4549623 or and equivalent. Now, disconnect the high-pressure hose from the hydraulic assembly. Be sure to wear safety goggles when disconnecting this or any other fluid lines. Next, cut all the tie wraps attaching the high-pressure hose, low-pressure hose, and wiring harness together. For visual clarity, some wiring harness connections have been moved aside. On AS body vehicles, you will also have to disconnect the high-pressure hose clip from the battery tray, as seen here. The following steps will demonstrate the high-pressure hose replacement procedure. First, on AC, AY, and AS body vehicles, disconnect the pump end of the high-pressure hose from the pump and motor assembly by removing and saving the banjo bolt. Remove the O-ring from the banjo bolt and clean the bolt. Next, separate the connector block from the pump and motor assembly. When performing this step, be careful not to disturb the pump end of the other low-pressure hose. The low-pressure hose is only retained by the internal O-ring seal. Now, remove the high-pressure hose from the vehicle. When working with brake system components, be careful to prevent brake fluid from contacting any painted surfaces. If contact occurs, flush the area thoroughly with water. After removing the hose, clean the pump contact face for the high-pressure hose with Mopar brake parts cleaner or an equivalent. Next, lubricate the supplied O-rings with brake fluid and install the large O-ring on the connector block face and the small O-ring on the cleaned banjo bolt. When working with brake system parts, keep your work area clean in order to avoid contamination of system components with dirt or foreign materials. Next, install the connector block end of the supplied high-pressure hose to the pump face with the banjo bolt and tighten the bolt to 10 foot-pounds or 14 Newton-meters torque. After installing the connector block to the pump face, route the high-pressure hose along the left of the low-pressure hose and over the low-pressure hose to the hydraulic assembly, as shown here. Again, for visual clarity, some wiring connections have been moved aside. Next, remove the cap from the fitting on the supplied high-pressure hose and install the end of the hose to the hydraulic assembly. Tighten the fitting to 145 inch-pounds or 16 Newton-meters torque. To replace the high-pressure hose on the BB Body Eagle Premier and Dodge Monaco vehicles, also begin the procedure by disconnecting the hose from the hydraulic assembly. For visual clarity, the air cleaner assembly has also been removed. Next, cut all the tie straps attaching the high-pressure hose, low-pressure hose, and wiring harness together. After freeing the hose, remove the bolt from the brake hose attaching clip and undo the spring clip with channel lock pliers. Next, remove the high-pressure hose from the clip and pull the hose clear of any obstructions so it can be pulled out from under the vehicle. Now, raise the vehicle on a hoist and from under the vehicle, disconnect the pump end of the high-pressure hose from the pump and motor assembly by removing the banjo bolt. Remove the O-ring. And clean and save the bolt. Again, being careful not to disturb the pump end of the other low-pressure hose, remove the high-pressure hose from the vehicle. Clean the pump contact face for the high-pressure hose with Mopar brake parts cleaner or an equivalent. Next, lubricate the supplied O-rings with brake fluid and install the large O-ring on the connector block face and the small O-ring on the cleaned banjo bolt. Now, route the high-pressure hose along the low-pressure hose up into the engine compartment, being careful not to twist the hose. Next, install the connector block end of the supplied high-pressure hose to the pump face with the banjo bolt and tighten the bolt to 10 foot-pounds or 14 Newton-meters torque. Next, lower the vehicle and finish routing the high-pressure hose to the hydraulic assembly. Now, reinstall the high and low pressure hoses in the brake hose clip and reinstall the clip attaching bolt to the shock tower. Remove the cap from the fitting on the supplied high-pressure hose and install the end of the hose to the hydraulic assembly. Tighten the fitting to 145 inch-pounds or 16 Newton-meters torque. The following steps apply to all vehicles. Begin by installing the supplied tie straps around the hoses and wiring harness at the locations shown in the illustrations in the dealer recall notification letter number 526. After properly tie strapping the hoses, on AS body vehicles, also install the supplied hose clip to the high and low pressure hoses and attach it to the battery tray. On ACAY body vehicles, the transmission tuning weight must be reinstalled. Next, on all models, reinstall the fresh air intake duct and the air cleaner assembly on AS body vehicles. Now, reconnect the negative battery terminal. Next, turn the ignition switch to the on position to start the brake booster pump, and apply the brake pedal several times to distribute the fluid. Next, turn the ignition off and pump the brake pedal 40 to 50 times until the pedal is hard. Now check the brake fluid level. It should be at the top of the inlet screen. If the level is low, add brake fluid as necessary using new Mopar brake fluid or an equivalent with SAE 1703 and DOT 3 ratings. Finally, start the vehicle and evaluate the brakes for proper operation to complete the service procedure. Dealers are urged to give their full support to this important program by serving all involved owners promptly and courteously, and by performing the service on all vehicles in dealer stock before retail delivery. For further information regarding vehicle lists, service procedures, repair parts, and claim reporting procedures, refer to the Dealer Safety Recall Notification Letter, number 526.